All right, so I think we'll go ahead and get started here. My name is Cass Everritt, and this is James Dolan. We both work as software engineers in the Mobile SDK team. We both are in Texas. He lives in Dallas. I live in Austin. And we're going to talk to you a bit about things that have happened in the Mobile SDK over the last year. And so sort of to give you a brief overview of what we're going to talk about, first we're going to just talk a bit about what the Mobile SDK is, hitting on the VrApi driver, VrApi 1.5. James will be doing those two topics. Then I'll come up and I'll talk to you a bit about the compositor and MultiView Rendering. And then James will come back and finish up with Oculus Remote Monitor and Snapdragon Profiler. So I'll give it over to James now, and I'll be back in a few.
Thank you, Cass. So I kind of wanted to start with a little bit of an overview of what we're going to be. Is this? I kind of want to start a bit with what the SDK is, what it's not, and just kind of make sure everyone's up to speed. The core of the Mobile SDK is a library called VrApi, and this is sort of the lowest level interface that all applications must use at some level to support Gear VR. And it takes care of things like sensor fusion and head tracking, as well as the compositor and distortion correction and time warp, as well as all the little low-level trickery we do to maintain low latencies and guaranteed performance. The sort of second piece of the SDK is VR App Framework. And we provide this because while it's not absolutely necessary, some people do want a higher level application framework that handles things like rendering meshes, playing sound, doing user interfaces, and so forth. And we provide this with full source code. It's small, it loads quickly, it's easy to hack on. And we use it on a bunch of first-party applications like Oculus Video, 360 Photos, Arcade, and even third-party applications like Netflix use it. So I encourage you to use it either as a reference or as an engine for your application. All right, that's a quick overview. So now you know what we're talking about here. Sort of the next big thing that we've done over the last year, and this kind of got released about a year ago with not much fanfare with 1.0, is the VrApi driver model. And this is something that we did to sort of help ensure forward compatibility with new hardware and new OS updates that came along. The issue was, prior to 1.0, VrApi was basically statically linked with your application. This meant all of the little tricks and hacks that we do to make VR actually work really, really good on Gear VR was baked into your application. So if a new Android OS came out, or a new driver came out, or just a new headset came out, if it had any issues, the application would have to rebuild to handle that. So we really wanted to fix that. We really wanted to make sure that applications didn't need to worry about minute increments in technology. So the way we did this is we bundled our driver into a separate APK that we could update independently. And this is really nice, has a lot of nice properties. It means that all the things we talked about before can be updated without going through an app developer. And more importantly, it means they can be updated without going through phone carriers, which means we don't have to wait months to get an update out. If we see a bug, we can fix it and we can QA it and release it as quickly as possible. So we can efficiently address issues as well as add new features. So for instance, video capture is something we deployed across the entire Gear VR ecosystem through an update. So now through the universal menu, you can sort of tap in the headset, start a video capture, record your game, post it on Twitter or YouTube or Facebook or whatever, and you can do that without actually building that feature into your application specifically. Now, the way this works is there is still a libvrapi.so that your application links to and includes in your APK. The only difference is that it's no longer containing the actual code of our driver. It's just sort of a loader stub library. So the very first thing it does when it gets loaded into your process is it goes out, finds the driver, and initializes entry points in there. And for those of you who are curious, this is actually very, very similar to the way OpenGL symbols get initialized on Android today. The only difference is that our symbols lay in a package we can update independent of the OS, whereas with the OpenGL driver, it's bundled with the OS image, which means you have to get a carrier update and reboot your phone and go through all that to update the driver. Now, all applications built against 1.0 and greater use this driver model. And this is actually why, in December of 2015, we required all new submissions to be built against 1.0, because we really wanted to make sure that applications had the best chance of forward compatibility. And this is how we did it. The other nice thing is that because we're able to update this so seamlessly, the vast majority of Gear VR users are on exactly the same version of VrApi. And users that download apps through our store are at least guaranteed to meet a minimum version. And this means, as compared to other drivers on the system, there is very, very little fragmentation. You only need to worry about basically the latest driver and the minimum version driver, which usually means you have to only look back about a month or so. You don't have to look back years in terms of drivers to check compatibility. Now, that's sort of something we deployed recently. And I want to talk a bit more about stuff that we're going to be deploying very, very soon. And that is VrApi 1.5. This is going to be a more API architectural update than direct feature adds, but there'll be a few new features as well. One of the biggest change that we're going to make is to the VrApi submit frame function. Now, we're going to bring this in line to look a lot more like the Rift SDK OVR submit frame function. And that is to mean, instead of the monolithic structure that you would have to fill out before that include everything from your layer descriptors to your eye buffers to performance parameters, you now are going to pass in a pointer to an array of structures of layers where the first 4 bytes of every layer defines the type. And this means you get sort of polymorphic behavior from those layers, which means if we come up with a new fancy layer format, may it be some new projection, Equirect, CubeMap, or whatever, we can just add that without disrupting the rest of the API. And Cass will sort of talk about some of that stuff later, and that's sort of leads into why we needed to redesign this API. We're also deprecating some older code paths. And probably the most important one to note is that the EGL surface will now be created by VrApi rather than by your application. Your application will pass in a window handle and will create the EGL surface. And this, again, is to help maintain forward compatibility as we have new devices come along and maybe have to adjust the parameters going into the EGL API. Now, on top of that, there's a few APIs that used to live in a separate library called system utils, and we're going to promote those into VrApi so that you only need one API to do the minimum required functionality for a VR application. No longer will you need several libraries. VrApi will do the basics of everything, and while we'll still provide libraries like App Framework to do a little bit more, you no longer need things like system utils. Now, most of these APIs are pretty simple. They're things like return to home or showing a fatal error. These are things that all applications must do under certain circumstances, but we wanted to make it really easy. Now, 1.5 is coming soon, but that's not it. Soon after 1.5, we'll be doing some under-the-hood driver architectural updates. One of the biggest ones is we're moving head tracking into a separate process. And this is important because we can avoid the sort of yaw correction snap you get when you switch applications, and it gives you sort of continuous head tracking between applications. It also allows us to implement new tracking technologies, which is very important, as you might have noted during the keynote. This won't actually require any change to your application. All applications built against 1.0 will switch to this new tracking service automatically. Next up is 64-bit support. This obviously will require you to build your app, but there's no API changes. The reason why we're so excited about this, though, is not about address space. it's about performance. In synthetic tests, we've seen very optimistic results from synthetic tests that show just switching your target architecture to ARM64, which brings with it new instructions, more registers, a program counter that allows for deep pipelining. You just get a free performance bump for it, and more performance means less power and less heat, or it just means more features. So we're very excited about this. And last but not least, Vulkan support. Now, this is still a work in progress. We're working with all the relevant IHVs, but we're seeing really, really promising results. And again, in synthetic benchmarks, we are seeing about a 7x increase in the number of draw calls we can handle. But of course, in your application, results may vary. The important thing to note, though, is that the very conservative guidance we're currently giving people, which is about 100 draw calls a frame, will probably go up significantly when they switch to Vulkan. Now, there's a few missing pieces from the drivers. Most importantly, we need multiple queues with different priorities in the graphics driver, as well as front buffer rendering access. And we're working with all parties to make sure this happens, so we hope to get this in the wild very, very soon. Now I'll hand it over to Cass to talk about the compositor and multi-view rendering.
OK, so one of the things that I work on in the Mobile SDK, one of the things that I've sort of spent a lot of time on, is the compositor, and we call it the Timewarp. But it's sort of a lot of things. And I wanted to sort of talk about it at a high level. Our documentation at the SDK level doesn't have a ton of information about it and what it does. But the way that you chiefly interact with it is this VrApi_submit frame call, and it's where you pass in data to the API to be displayed. In a conventional 3D graphics API, this would just sort of be where you call swap buffers or present or whatever. But the interesting thing here about it is if you look at the diagram, we have basically the application, when it's beginning its rendering process, goes, and this generally happens at some long latency, say tens of milliseconds, call it 35 milliseconds, before the images are going to be displayed. It goes and asks, what is the current predicted orientation and position of the head? And it goes and draws images left and right that correspond to that predicted orientation. And so that part is what the app does. And then inside this little dotted box is where submit frame happens. And now the Timewarp or the VrApi compositor has those frames. They're not yet finished rendering, and that's why we have to have a sync fence available with them. But then what we do is we look at it and say, OK, so these frames are ready to be displayed, or maybe they're not ready to be displayed. We'll check the fence to see if they are. But we find the latest ones that are available. And then we go and do another prediction for that particular display time to see if to see how much error there was in the prediction that the application got tens of milliseconds ago versus the one that we have now just 8 milliseconds away from display. And 8 milliseconds is just a particular number that we use for Gear VR. Different displays would have different numbers there. But what happens then is that we go and make adjustments for the difference in the prediction error, and we get a better prediction, even though it's still a prediction, it's closer in. And we do this sort of, these arrows here sort of indicate that we move the scene left or right or up or down, depending on what the actual error is, to correct for it, so that things show up in the right place in your virtual world. And the other thing in this image is you can see that we apply distortion correction there. And that's an important aspect of what the compositor does as well, because the lenses that we use just sort of necessarily have this pincushion distortion. But again, the compositor does this distortion correction, which includes chromatic aberration correction. It takes layers from the application, and this is something that didn't get used in the very early sort of parts of the very early apps for the VrApi. But it turns out that being able to have layer support where the app can have multiple sources really addresses a sampling density problem that I'll talk about in just a second. So you can use layers to really good effect, especially for things like text readability. And then the system, when you press the volume up and down rocker, for example, the system will give you a notification to tell you that that's happened, and that happens through the layer system of the compositor as well. So I want to take a second and talk about some of the new features that we've added in the compositor. But in order to do that and sort of motivate why they're there, we have to take a brief aside to talk about sort of the way that sampling works in 3D rendering versus the way it works in VR. And the big thing to note here is that when we're rendering to a monitor, we basically have this nice planar projected straight lines sort of way of looking at things. And so if you were rendering a map like we see here, things look normal. The problem is that when you add the VR lenses, which give you this great sort of immersive effect, the problem is that the lenses themselves create a pincushion distortion. And now, in order to get a fully rectified image, something that looks like reality, we have to go and imply an inverse distortion so that things look correct. And that process has a number of sort of side effects. One of the most important is that planar projection, if you haven't spent a lot of time thinking about it, planar projection actually is interesting in that it samples most poorly directly in front of you. So in terms of the angular separation between pixels, the largest angular separation is directly in front of you, and the lowest angular separation is out, at the periphery. So we're wasting a lot of pixels on the outside, and we don't have enough on the inside. So one interesting sort of artifact of this barrel distortion that we have to apply is that now we're also stretching out that section where we don't have a lot of pixels in the center. And this sort of can exacerbate a problem of legibility of text and things like that. And so we take great pains to correct for that and to apply features like, for example, layers, so that you can put a smaller image that's right in front of your scene, and it's not panoramic, it's not like really in the wide field of view, but it's got great sample density and it looks great on your display. Okay, so, but we're going to talk now just for a second about two new layer types that got added in. And these layer types got added in using an extension mechanism that was sort of cumbersome and is what motivated the sort of switch that VrApi 1.5 will have. Everybody knows what equirect here is, I assume. But basically, the idea is that you have constant latitude in rows and constant longitude in columns, and that these latitudes are evenly spaced and the longitudes are evenly spaced. And so it winds up looking something like this globe. And each of those little squares in the wireframe globe picture there corresponds to a single pixel. And that all makes sense, and if you saw a map sort of laid out that way, it would look like you would expect it to look. But the problem is when you look at an equirect projection, it has this sort of telltale weird layout. So we're looking at a hangar or a sort of a warehouse space with an airplane in it, and there's sort of a grid on the top that's if you were standing in the room, you would look at it and you would see it sort of everything is made of rectangles. And the problem is that the equirect distortion makes that completely non-obvious when you're looking at it. And so it has this sort of strange concentric arcs that they intersect at 90-degree angles whenever you look at them, but it's sort of a strange looking view. And we spend a lot of pixels at the North Pole and a lot of pixels at the South Pole, probably where you're not looking. And then we have the worst pixel density right along the equator, probably where you are looking. So while it covers the whole space, the main value of this format is that it's what everybody uses. So love it or hate it, it's going to be one that's there. So we provided this as a layer source mostly because if you have data in this format, the best way to see it is to just pass it directly to the VrApi and say, sample this directly at screen resolution. It does not make nearly as much sense to render it to an iBuffer and then you get the sampling error from that and then display that. Okay, but because it does have some other less satisfying properties at the poles. We also added a new mode for things that can kind of work really well, like text rendering or menus and things like that. It turns out that cylindrical is sort of a nice format for those kinds of things. And cylindrical is not horribly dissimilar from spherical. It's constant latitude, but they're unevenly spaced, and the evenness of the spacing is basically that in the vertical slice, it's just like planar projection. And then the horizontal slice, it's just sort of equal angles. So longitudes continue to be spaced evenly, and they're constant longitude lines vertically. And so if you look at the same image as before, you can sort of look at the ceiling now and tell, there's definitely a scene, the ceiling is full of rectangles. And things kind of look like rectangles in this view. And that's great, but one of the problems with cylindrical, which I don't know if you can sort of tell it immediately, but we kind of can only go plus or minus 30 degrees before the distortion from the planar projection gets bad. And planar projection just isn't great for expressing a really wide field of view. But for things that work well at plus or minus 30 degrees, cylindrical is a really nice layout. Okay, and then there's one more format, and this new format is based on when we first added layers to the compositor. The obvious first one was when you render, you get eye buffers. So we had 2D texture sources, and then for 3D photos and things like that, it was really obvious that yes, we just want to sample those directly in the Timewarp. So we added regular cube maps as sources for the Timewarp. But the problem with regular cube maps is, while they're great for photos, they actually turn out not to be super great for videos. And I'll talk about that in a second. But to motivate this, I want to show you what the mapping that we use for off-center projection cube maps is. And basically, normally you would texture from a cube map by calling the texture function with a cube sampler and pass in the direction that you wanted to sample in. And that's what the hardware supports, and that's what you would normally do. With off-center projection cube maps, you call the texture function with the cube sampler, but it's a special cube map that you have constructed with this off-center projection layout. And so, but the nice thing is this forward mapping, basically, all we do is normalize the direction and apply an offset vector, and then we look up into that cube map. For those of you that haven't seen cube maps in baseball cover sort of layout form, this is one that I like to use just because it's nicely compact in a 3x2 kind of layout. But basically, baseball cover is two pieces of continuous fabric that cover a sphere, and this is sort of two 3x1 rectangles that cover a cube. So at the top, we have left, front, and right, and so that's basically left, front, and right. And then the bottom row is top, back, and bottom. And so, so this layout, you can see, this is what a cube map looks like. And so the interesting thing here, when you're thinking about, and I want to particularly point out, this was motivated largely for 360 videos, because we really like the idea of being able to stream 360 videos to people, but the problem is that you can only look in one direction at a time, and if a video is playing and you're facing front, then we're having to stream all the pixels for left, right, up, back, and down to you, and then just throw them away because the next frame comes and you didn't look at them and you couldn't have. So that's sort of a waste of bandwidth and unfortunate. And so the 360 video guys had started looking at things like pyramid projection, and we sort of went down this route of trying to think of what we could do with cube maps to get the same kind of effect. And the interesting thing here, and I'm just going to show you an animation of what a cube map normally looks like, and this is a really low-tech animation where I'll just step through multiple slides with different offsets. But the idea here is that we're going to move the offset such that we get a better and better view of the center of the front face. So we're going to walk through, and you'll note that each time we move forward, we're getting all the same pixels as before, it's just more of them are focused forward. And I don't know if you can see this now, we're really getting sort of zoomed in on just above the airplane there in that office. And now we have tons and tons of pixels just focused right on directly in front of you. And if you needed to have something legible at this point, and you can see we're getting upsampling, bilinear sort of artifacts here. But if we had pixels there, they would be as sharp as you wanted them to be, which is kind of cool. And then just to sort of show how ridiculous it can get, if you go all the way to 0.99, and this is because this is sort of a radius of 1. You can't get past 1 without being outside the sphere, and then the mapping doesn't quite work. But anyway, so now you can see at this ridiculous level, half of the image, half of the cube map is taken up by something that corresponds to just a couple of square inches directly in front of the field of view. As a practical matter, we wouldn't want to do it that way, but it's sort of nice to understand how this mapping behaves. And I'll go through one more time just so you can see the transition. It's magical. Okay, enough of that. So the other thing that I'm supposed to talk with you about today is multiview rendering. And this is an extension that I worked on with hardware vendors that we talk with in Kronos. And basically, it's an extension that was meant to address a big problem that basically everybody in VR has. And that is, when you do VR rendering, it almost always needs to be stereo rendering, or you don't get stereo disparity and the feeling of 3D. And the problem with that is that the way that we communicate with the hardware and with the driver is exactly the same, or very nearly the same, for each frame, but we pay essentially double because there's nothing special that the driver can do to know that we're about to render exactly the same frame. So we added an extension to OpenGL that basically says, set me up so that I have both views configured, and then just draw once, and we'll draw to both render targets, both views at the same time. And that saves us on driver overhead, it saves us on application overhead, because we don't have to traverse the scene twice and send the graphics API calls. And there are also advantages that can be had in the tiler space, and some of them are you might only need to be able to do the tiling process once. Others might be, and this is something that may or may not happen, but it's something that I think is interesting to note, is that if you look at the actual squares of these hypothetical tiles, the geometry in them is pretty close to the same for both. So if you went and tiled for 2 views for the same tile at once, and then just rendered the same geometry to both of them, you'd have a little bit of overhead, but not enough to be, I think, really a game changer, especially for stuff that's like anywhere past 10 feet away from your eye. So the way that you use OpenGL multiview rendering is that you bind this new kind of FBO. And with this new kind of frame buffer object, you attach, as the color attachment and the depth attachment, texture arrays instead of just 2D textures. And then when you're rendering with this, you use shaders that have a built-in called GL underbar view ID underbar OVR. The name spacing there is a little bit gross, but the idea is the view ID is what you get. And you use that information to affect the position of the vertex. So in C++, you use this new function called GL frame buffer texture multiview OVR. That's how you create a multiview frame buffer. And then somewhere in your vertex shader, you make use of that view ID parameter to affect the output vertex position. A couple of things that I think catch people, if they're not careful, is we didn't actually specify what should happen with GL read pixels if you bound a multiview frame buffer for reading. So we just said you can't do it. So when you bind frame buffer with multiview, it has to be a draw frame buffer. Just be aware of that. The other thing is there's no enable or disable. When you have a multiview frame buffer bound, you are multiview rendering. There's really sort of no way around that. And it's always on, and that means that you need to sort of be careful to if you need to render to only one viewport, then you need one of the eye transforms to send everything to 0, for example, to make it degenerate. Or pick some other way to get stuff so that you can render it only to one eye at a time. But generally, I think the thing is the advice is just to the extent possible, make regular scene rendering work with multiview and make any sort of workarounds be the exception. The other thing that you could do is you could take these same render targets and create new FBOs where you render only to one element of the texture array. That's going to cost you some performance too, so again, focus on how to make multiview work all the time. And the names of these extensions are OVR Multiview, which is the first one that we made. It basically says that you can change position and nothing else. Multiview 2 says you can change anything, so if you wanted to have view-dependent reflection vectors, that's allowed in Multiview 2. And then if you need to do multi-sampled render to texture, that comes with a separate extension because the mechanisms for doing the mechanisms for doing render to texture required render buffers, which have sort of gone out of vogue, and we needed a new way to express them with texture arrays. And I think that's it for me, and back to James. Okay.
Sorry, guys.
You want this one?
Yeah, sure. Okay. And I'll get you another one.
Hopefully this is, okay, there we go. Hopefully this is working better. So yeah, I want to finish this up to talking about making developers' lives easier. Developing VR content is really, really hard, as probably everyone in this room knows. And we really want to make it easier. And while the Android tools landscape is a bit spotty, we've been working hard to make it a little bit easier for developers. And one of the ways we're doing that is with a tool called Oculus Remote Monitor. This is something we put out about a year ago, but I've been doing steady updates based on feedback. So feedback is welcome. And one of the big goals is making it easy to set up and use, because most developers simply won't use a tool if it's hard to use. So with Oculus Remote Monitor, we wanted something that could be used on a daily basis without much fuss, something you could just attach to a process while it's running, capture some data, monitor stuff in real time without interrupting your existing workflows. And sort of the idea behind it is to gather the 30,000-foot view of your application and the driver, not to dive super deep into things that require hardware-level access or driver-level access, but give you an idea of where you should look next. And so we kind of focused on low overhead of data capture and a real-time view of the data stream. And this turns out to be useful not just for performance analysis, but for statistical debugging and monitoring playtest sessions. The client is available for both Mac and Windows, and it works on all 1.0 apps without changes. We capture data over Wi-Fi versus ADB or USB, and this makes it really easy to avoid tethering to your device when you're in VR. And we discover remote sessions automatically. So you run an app, it's on the same network, it just pops up in a list, you can connect to it. And to give you an idea of the sort of data we could collect is first off, we capture a sort of a thumbnail-sized screenshot of every frame. And this is really good for when you go back and you look at your performance spikes or issues, you can see what's going on in your game, where you're looking at a particle effect or an explosion, or maybe it's just when you look at that wall, something bad happens. Now when you actually go and look at your performance data, you have a good idea of what happened. And so you can reproduce it later when you're looking at deeper level tools. We also capture VSync events for the choreographer, and this is useful for understanding when things happen relative to scan out. And it also helps you see when the kernel is maybe being interrupted and it can't deliver VSync events in time. There's a sort of experimental GPU timer query support. Right now, this is mostly just useful on devices that it works on for monitoring when Timewarp is actually executing on the GPU versus when the draw calls are executed on the CPU. We, of course, have CPU performance zones, which are manually placed in the code at strategic locations. And again, this lets you know when things like Timewarp are running or various other expensive operations. We capture logcat for our entire process, and we actually annotate it in the graph so you can see when a print statement happened in time and on what thread and relative to other events. There's also CPU context switches, which we grab from the kernel, and this lets you know what core your CPU is on and if it's asleep or it's active and so forth, and how it relates to other threads in the process. This is very useful when you have problems where maybe you have your game thread is having issues, but you can discover with this that it's switching cores all the time because it's getting interrupted by another task. We, of course, capture things like head tracking and CPU clocks and so forth. Basically, all the high-level bits that we know about in the system. There's also an optional library called libvrCapture. Now, you don't have to integrate this if you just want basic information I showed you above, but you can integrate into your application to put application-specific data on that graph. For instance, maybe you want to know when your character simulation happens or your physics simulation, or maybe you want to see when you're traversing your scene graph for rendering. You can use this library to annotate those scenes. There's also other cool features like putting in remote variables that allow you to tweak things like maybe your player height or lighting intensity in real time from the remote tool. The other cool thing is this library doesn't actually require it to be a VR application. If you wanted to integrate this into your engine, you could actually connect to it even if it's not a VR app, although it's mostly geared towards VR apps. Now, because doing a demo that involves a phone and a computer and a projector and all that stuff is difficult, I kind of did this offline. But here's a quick little demo of a session. The first thing I want to show you is basically how you enable capture. For security reasons, we don't have it always enabled. We make you do it through the tool so that only developers can do it. But the basic idea is you attach your device to USB for the first time, you select it, you enable capture. Now capture is enabled. At this point, you go back to your phone, you launch the app in question, and it will automatically populate in the tool as soon as it's discovered. At this point, you can just click on it, connect, and instantly the data stream comes through. It automatically gets saved to a file, so if you want to go back to it later, but you can monitor it in real time. And the cool thing here is even though we're collecting data in real time, you can sort of move back and forth in time, zoom it in or out if you spot an issue. Maybe it turns out to be non-issue. In that case, we're just looking at some draw calls. And then press the space bar and you continue the real-time view. Now, Oculus Remote Monitor, as I said, gives you that high-level view. But what if you decide there's an issue that happens at a very precise moment, and we're not able to give you the reason why it happened, just where it happened? This is where IHV tools come in really handy, because they have access to things like GPU stage timings or hardware counters that are just not available in public APIs. And so I want to talk about one today, which is a Snapdragon Profiler. Now, with a Snapdragon Profiler, you can connect to your device and see a real-time view of counters and clocks and so forth from the device. Everything from GPU utilization to number of draw calls, the number of vertices transformed to frame. You can use the snapshot view to record every draw call from a single frame, including all the resources that are used. This is really useful not just for debugging graphical issues and so forth, but also just verifying that your application is doing what you think it's doing. Is mapping really on? Are your textures really compressed? Is your GL state what you expect? This is very important for performance, because oftentimes in a complex engine, things are not doing exactly what you think they're doing. And last but not least, with the trace view, you can look at CPU scheduling events, just like an OVR monitor, but right next to GPU stage timings, which tells you not just how long things are taking on the GPU, but when they're being executed. So in this case, you can see that there's basically sort of a left eye, right eye render, and then a left eye, right eye render, and then there's sort of like this sort of time warp execution happening. And this lets you know basically that, yes, this is how long things are taking, and this is where things are happening relative to each other. And in some cases, you'll see time warp preempt your app rendering and so forth. Now, Snapdragon Profiler has a few caveats with Gear VR. Right now, we only have it working on production Note 7s with Snapdragon. And it requires you disable asynchronous time warp and front buffer rendering when you're actually capturing. But these are pretty small details for how useful it is. If you want to disable front buffer rendering and asynchronous time warp, on the shell you can just execute it, use 2 lines, and it'll disable it. You'll have a pretty bad experience in VR when you do this, but a lot of profiling tools start working. Now, I don't want to dive too deeply into Snapdragon Profiler because I think Qualcomm in this room right after us has a session on all of their tools and how to optimize and so forth. So I suggest you go to that if you're interested in profiling at all.